Hi everyone. I'll just wait a few more minutes to see someone is joining, then I'll start the class for today. For this week, we'll be looking into the assignments based on the data analysis part, which was on full circuit models, etc. Okay, so we'll start with a short recap of what we have seen in the last class, and then so in the last class, we were looking into data validation. So in data validation, we were looking into KKT models, then when we have to go with impedance data, when we have to go for admittance mode, and then challenges in KKT, and then the application. Finally, we also started with measurement model approach. So where we are using the passive elements like resistor, capacitor, inductor, and all to model the circuit. Sorry, model the impedance. And yes, so we're going to look more into that aspect today. So we saw that the impedance it should be repeatable, it should be linear, it should be stable. So repeatability was means you have to get the same reproducibility. Linearity means when you increase potential, there should be same way an increase in the current. So overall, the impedance data wouldn't change. So we also saw the regime like what amplitude we must give in order to have a linear behavior. We also saw small amplitude causes noise, large amplitude causes non-linearity, and there is a optimum, I mean not optimum, but there is a range at which you can actually give the amplitude so that the system remains linear. And finally, stable. Stable meaning the experiment, it shouldn't drift from the potential value or the current value at which the impedance is done. And then we saw the validation, which was KKT, which actually shows if your system is linear, causal, and stable. Those are only sufficient conditions. They are only sufficient conditions and not necessary conditions. So satisfying KKT doesn't mean that they are actually linear. They are linear, stable, causal. There can be chances where they are non-linear or unstable, where it can be flagged as KKT compliant again. Then, yeah, then we saw a few examples where the system is behaving like how the KKT will be flagging the system if it is unstable, non-linearity comes, etc. This all we saw in the last week, and then we also started with assignments. Yeah, and finally, we were going to see how we are able to model the system using resistor, capacitor, and inductor. So, yes, I'll start the next class. So, this chapter is more on data analysis part. So, I'll just write what you have seen in the last week. So, this class by today is 21st. So this week we'll be seeing more on introduction to equivalent electric circuit, EIC is equivalent electric circuit, then choice of circuit, then confidence interval, initial values, distinguishability, zero and pole representation, RT, RP. Then we'll be seeing the types of circuits, some well-known circuit. One is Maxwell, then Void, ladder circuit, then yes, then we'll be discussing the science. So this is about today. So what why we are using the passive elements like resistor, capacitor, and inductor. So once we obtain the impedance data, if we don't have over the entire range of frequency, maybe because of the low frequency regime, the data becomes very noisy or the system is unstable. We will be actually chopping off the range of frequency in which we can get the data. So if for such a system, if you're going to do KKT, it may flag it off as KKT non-compliant because we don't have the data over the entire range of frequency. So in such a case, an alternative is to model it using passive elements like resistor, capacitor, and inductor. So yeah, so if we are able to model the system using these passive elements, we can obviously say that the system is KKT compliant. So that is where modeling the system using passive elements come. So here we use passive elements like resistor, capacitor, and inductor. So this method is called measurement model approach. So an introduction to this was given in the last case. Yes. So in a what to say in measurement of model approach, we can make use of the the void circuit like R and C in parallel in order to fit the data. So the number of elements that we are going to actually use to fit the circuit, it depends upon how good the fit is. Based on that, we cannot use. So it depends upon the error that we get that we'll see in the coming, like as we talk in this session. Then what do we have to see? We will see the types of circuit. So here we have to see the type of circuit. I'll be introducing to the type of circuit before itself, so it becomes easy for everyone. And then we'll move on with the other topics. So the easiest one is a void circuit. So in void circuit, we'll have a capacitor which is in a parallel with a resistor. Okay, it is a simple RC circuit. They are in parallel, and many such RC will be in series. So, and we also have a resistor in the beginning. So this we have seen in the first or second class. This is nothing but this is the solution resistance. So everything else we'll be using to model the system. Okay. Uh, So, although void circuit consists of only R and C, it can be also used to model the system that comprises of an inductive behavior. Inductive behavior meaning where the Z imaginary minus Z imaginary is again becoming a negative. So in those systems also we can use void element or the diffusion aspect is there. So all those can be. So I said void element can be used to model the system which can be arising from a inductive system. Inductive system is something like this. So this is an inductive behavior, we know. But then how can it be modeled using RC? So the only condition here is that when we are using RC elements to model an inductive element, we should allow the capacitor to become negative. Capacitor and the resistor to be negative. So in that case, it can be used to what to say, R and C must be allowed to become negative, so it can model the inductive behavior. So now we have some circuit. We will be trying to fit it to the this what to say capacitor, inductor, or resistor together and try to improve the fit. But how many such circuit that we need to? For example, I have something like this. Imagine how many such elements do I need in order to fit this? So I cannot keep on adding. So obviously, if I add more and more, fit may improve. But when can I say that these many are not needed? So it depends upon visibly we can say with the fit, but apart from that, we should look at the error. Like as you keep on adding the element or that circuit, is there a reduction in the error? Or is it those elements having very high error? So that determines is that actually needed or not. So for example, okay, I'll just I have a circuit like this. So the first question is how many such how can I fit this? So you see it is a two semicircle. So we can obviously say there are two loops. Two loops meaning I'll need at least two what to say RC elements in order to fit this. Okay, that's how we usually say that. So at least two. Okay, at least two I need to fit it. Okay. Now what will happen? So we use a software called ZSIMWin in order to fit the impedance data using the passive elements. We use that. There are other softwares as well. So if I fit it using, for example, I tried fitting using this circuit. Now after this in ZSIMWin software, you will see there is a tab where you can actually see the error. Say this is R1, sorry, C1, R1, C2, R2. So here I've assumed RS is 0, solution resistance is 0. So it doesn't need a this thing in parallel. I mean in series because this is already 0. So I'm not considering this. So this one, now once I finish fitting it in Z7 software, I can see what are the values of R1, C1, R2, C2. Okay. And apart from that, there is a what to say a column called error. This says the values. So here it says initial value, there will be initial value column and final value column also. Apart from that, there will be an error column. So ideally this error should be less than 20% is what we wish is to have it less than 5 to 10%. But in some cases it may go up to 20, but more than that we may have to think. So this will give you an error. So imagine So I told if the fit is good, all this value should have an error with less than 10%, or sometimes we depends upon the fit, we may go for up to 20%. Now, if for instance, to this circuit, okay, I am trying to now fit it using three RC elements in series C1, C2, C3, R1, R2, R3. So now to this circuit, if I try to do the same fitting using ZML, and I'll again look into the error. Okay, R1, C1, R2, C2, R3, C3. Okay. So now this error is normal. This like you may get something around to the case where you got it here. Okay, almost same like that. You'll get 5, 7, or 2, 3. Now, sometimes what happens is R3 value will be 100%. This one will be 500%. This means the error is very high. And in that case, error is high means something above 20. It depends again on the fit. Over the time, you'll understand. But something above 100, 200 and all, it's obvious that it means the error is very high. So if the error is already very high, why do we need to use that to fit that? So that condition or that situation when the error is very high, we get to know that these are not needed. Why? Because when you fitted using 2 RC, your error is already low. Now, when you came to 3 RC, you see if the first four are having a nominal error, and after that, all of a sudden, this becomes very high. This gives an indication comparing the 2 RC and 3 RC, you get to know that this becomes kind of unwanted. So, based on that interpretation, you get to know that only 2 RC is needed in order to fit this. So, this is how, over the time, when you're doing it again and again, you get to know if how many circuits you need in order to fit it. Sometimes, what happens is the loop will look something like this. Visually, it may seem like a single one. Okay. So in these cases and all, either you may have to look into the Bode plot because in Bode plot you will see phase change, not phase change, phase or magnitude slope change. You understand that there is a more number of loops. Sometimes they are also it won't be visually understandable. In that case, when you do it in ZSIM, you from the error value you can understand if this can fit using two circuits or is this actually having two loops here. So this is how by fitting the data using passive elements we get to know how many circuits are there, how many RC elements are there, and based on that we can get a good fit. And by validating the error we'll actually know if the additional added elements are required or not required. Yeah. So now let us look in. So this is void. Shall again draw. So this is solution resistance. You have many such RC in parallel. Okay. RL, CM. This becomes your point. Now the next one is Maxwell. Maxwell, again you have the solution resistance and you have a capacitor and another resistor. Now after this you have a resistor. Sorry, I think have been thrown out. Yeah, sorry. Yeah, I think my voice is audible, right? Something had happened, so I just yeah, the slide is visible, right? So Maxwell, how it is? You have capacitor and a resistor in parallel. After that, you have all the capacitor and resistor in series. So like this, you will have multiple of them. You will have multiple of them like this. This becomes Rn and Cn. So this is the double layer capacitor. So when you have multiple loops, you usually assign the first loop to the double layer capacitor. Okay, first loop might be a combination of double layer capacitor. Sorry, the first loop is always attributed to the double layer behavior, or sometimes the loops can be merged. So on this here also I can say this one is CDL. Okay, so this part, sorry, I have to make a change. Uh, in Maxwell circuit, I will say this is solution resistance, this is double layer capacitance. Okay, and I've shown you in the first class where for any circuit, you have double layer capacitance, and this one represents the Faraday reaction. This solution resistance. So this entire part, this entire part becomes the Faraday reaction. Okay. When it comes to void circuit, I cannot differentiate double layer, or I cannot separate out double layer capacitance from the Faraday reaction. Why? Because I have one C1 here, another R1 here. I cannot say this is ZF. Then what is this entire part? So the problem when you're using void circuit and fitting the data is you cannot group the double layer capacitor and separate it out from the Faraday equation. Whereas when you're using Maxwell circuit or ladder circuit, it becomes easy. So this is about Maxwell circuit, and the now the next one is ladder. In ladder, same like this, you have solution resistance and CDL. Now after that you have a resistor. You have the next capacitor here, next resistor here, again a capacitor, again a resistor, and it continues. Okay, this is how you get a ladder circuit. So basically here they are in series, here they are in parallel. Okay, so this is RS, this is CDL, and this entire part corresponds to the Faraday reaction. So, so this is how we represent in a Maxwell as well as the ladder circuit. Okay, I hope this part is clear. Now the next one is fitting. So you have minus z imaginary, z real. You get something like this. So this is a single loop, and you can fit it using a single RC. Now, if I have something of this form, how will it be? What is the difference? Difference here is here it starts from 0, here it is little away from 0. And that difference or the distance from the 0 to the point where it starts, forming the solution, the semicircle, this is the solution resistance. So this solution resistance is always represented using a simple resistor, and then you again have a resistor and capacitor in parallel. Now let us move on to the next case where you have two loops. Okay, in two loops, when you have two loops, you have to keep in mind you have two RC. So two RC, this can be either fitted using a void element. So in void, you'll have something like this. Okay, this one. Or you can also fit it using a this. This represents one loop. This is the next loop. Or this can be also fitted using this one. So so either this one you can use this one. This is the void. This is Maxwell, and this is ladder. So it's one same circuit. It can be fitted using three different types of circuit. So this property, or this is what in the lecture it's called distinguishability. You are able to fit the same thing using multiple loops. The only thing is that the value of the resistor and capacitor in each of the circuit will be different. If I say C1 here, C2 here, C1, C2, C1, C2, the C1 in void will not be equal to C1 in Maxwell. This again will not be equal to C1 in ladder. So distinguishability is where you can use different kind of circuit in order to fit it. So they can be used interchangeably, but the values of the resistor, capacitor, inductor that is used in the system will not be same in each of these circuits. So that is about the distinguishability. Now let us go to a case when there is three loop. So in again, if you have three loop, we need three RC elements. So either three void of RC, or you can go for Maxwell, where you have okay, I'll draw. Either you have you can go for what to say void like this, or you can if I have three loops, it means three RC circuits. So either this one, or you can go for the Maxwell circuit like this, where you have three pairs of RC, or it can also be, yeah. So either this Maxwell or this ladder or this void circuit can be used, and except that the values will keep on changing. So the what to say the if you multiply one R, this R1, RC1, similarly R2, C2. So R1 and C1 are a pair. R2, C2 are a pair. They form a pair. R3 and C3, they again form a pair. So that R and for any value. So this multiplied product, sorry, the product of R and C, it is called the time constant. So if the time constant are very different from each other, you will see two separate loops if there are two RC. But if toe 1 is very close to toe 2, there are chances, toe is nothing but the time constant. There are chances you will see them merged. So this something like this. So it's difficult to say. So in that case, you have to try fitting and understand if it's a single circuit. So if it is one circuit, the error will be high. Two circuit, the error will be lower. So we can say that you need two RC circuits to fit it. Okay. So if you go for one R1 and C1, the error is high. If you are fitting it using Z7, when you go for R1, C1, R2, C2, error of the components reduces, and you say that the fit is improved. This case fit improved. So these are some things you have to understand. Now the next one is, so the question is, how many elements should one use in electrical circuit? So how to find that out? So there is when, that is when you'll see AIC coming up. So I'll write a little. So circuit with minimum number of elements that can fit the data well is what is preferred. Okay. So you can identify this by calculating the residue. So what is residue? Sum of square of error between model and experimental value. So as I had shown here, you keep on adding more elements, you see that the error is very high. This is experiment, not experiment, what to say, using a software called Z-Submit. But otherwise, if you are doing it by hand, what you have to do is you have to take the error between the model and the experimental value, square of the model and experimental value. So when you're keeping on adding the RC elements or any passive elements, and the error after a point does not decrease, but it keeps on increasing, that you understand that previous case you have to take and say this is a maximum full. So when adding more number of elements, do not result in significant reduction in residue. It can be considered adequate to describe the data. Alternatively, so this is one way of calculating the residue. Okay. Alternatively, for each addition of another element, I can keep on adding penalty and see how the value comes. Okay. And that method is called AIC. AIC is nothing but it is archaic information criteria. So this is the first one. You're calculating the error between the model and experimental value. If you are keeping on adding the value, it doesn't bring down the error. So we say the sufficient number of elements are used to describe the data. Otherwise, we can use AIC, which is archaic information criteria. Just give me a moment. Yeah. So it is archaic information criteria. So here what you're doing, you're adding penalty for the addition of each number of elements. And the formula is AIC equal to 2K plus N ln RSS, which is a residual sum. So here N is the total number of observations you have. K is the total number of independently adjusted parameters in given model, and RSS is equal to residual sum squared value. So what is happening here is when you're adding more number of elements, you're adding up the penalty. And so what happens is when you're adding more number of elements, uh, you're adding up, you're actually the sum, right? So when you're adding more number of elements, you're increasing the value of AIC. At the same time, you try to reduce the residue. This value keeps on reducing. And so you in one way you're adding the elements, in other term you're reducing the residue. So how will the value of AI information criteria come. That is what you're looking at. So adding more elements, what will it do? It will increase AIC, and it will also, so at till a point, adding more elements tries to reduce RSS value, the residual sum of squares. So at which, so one term it will reduce a RSS and thereby reduce the AIC value. Another term, adding the number of elements, your AIC value increases. So one term causes an increase, other term reduces. So in that, after adding so many elements, at what point you get the minimum AIC? So these both are like counteractive, which both of this are like trend. One increases, other reduces. So what do you finally look for? We look for minimum AIC. Okay, so that is the case where we say that yes, these many number of elements we have added, we have minimized AC. Yeah, this is the best fit you can obtain. Now there is another called modified AIC. So when your observations are small, so like the n by k is nothing but the total number of observation by the total number of independently adjusted parameters. If this is less than 40, then we use a modified version of AIC. Okay, and this can be written using AIC corrected equal to AIC plus 2k into k plus 1 by n minus k minus 1. So this is, so this is just the information. Now, then the error is very large. That means we cannot be confident about the predicted value. Yeah, this value you have fitted it, but if the error is high, how can I be confident about that value? I can say poor. Circuit, visibly, the circuit fit will be good. But the error high. So in this case also, we cannot rely on the fitted values. It's not always on the visible visually what you do, but the error wise, if it is very large, we cannot rely on that data. We have to look for an alternative. Okay. Now, yes, there is something called distinguishability. Distinguishability, as we mentioned, same circuit as what we say, the impedance data can be fitted using multiple circuit. And I also mentioned that the only thing is that the values of RC used in all the circuits will be different. So that's why we are able to interchangeably use it. But irrespective of what that nature of circuit is, be it void, Maxwell, and the Max- Maxwell Voigt and ladder, if you are interchangeably able to use it to fit the data given, the total impedance of that system is going to remain as what to say, constant. That is what it means. Now, if I give you an example, okay, we'll look into the next topic, which is distinguishability. Okay, so one circuit is this one. So R1, R2, L1. we already saw if we have an inductor in the circuit can be still fitted using an RC circuit. The only thing is we should allow that R and C value to become negative. So this means the same thing can be fitted using a capacitor in parallel to R1, and then you have another resistor. Right? Just replacing this inductor with this capacitor, we are able to fit the same circuit. Okay. Now this same thing can be again fitted using another one. So that what I've done is I've taken out one resistor outside and placed it. Let's say R5, C6, R6. And again, this can be again fitted using something like this. You see how we did here. We're taking out the resistor here, and we're allowing the inductor to be allowed. All these are can be used interchangeably, except we can say that the total impedance. Okay, so the total impedance over here will be equal to the total impedance here, should be equal to that here, and should be equal to that over here. So by using that condition, we'll be able to bring out some relation using what to say the elements used here. I told the values will keep on changing. It's not same. So in order to study that, before that, we should also know what is RT and what is RP. So one is a charge transfer resistance and one is a polarization. This part I'll be explaining to you once I'm solving the assignment questions. Okay, which I'll be doing in a couple of minutes again ahead. So before that, when I'm going to do it, I want to know what is RT. RT is charge transfer resistance and RP is the polarization resistance. So for example, the value you get when the frequency tends to infinity, that is at high frequency regime, whatever value of impedance that you get, that is corresponding to the charge transfer resistance. Similarly, when you have omega tending to zero or the low frequency regime, the value of impedance that you get is nothing but that is a polarization value. So this can be written as RT limit for a potentiostatic mode. So you're doing it at a constant DC potential. In that case, the EAC naught tends to 0, limit omega tends to 0. Sorry, not 0, it is omega tends to infinity. Whatever value of impedance you get, that is. So in short, this is what it means. Omega tends to infinity, value you get is RT, omega tends to 0, whatever value you get is RP. So in terms of potential static and galvanostatic mode, ferrite, this galvanostatic. Same way with RP, so the same EAC naught tends to 0, then limit omega tends to 0. Whatever you get, that is the RP value. Then IAC naught tends to 0, limit omega tends to 0. Z. This value is called the polarization resistance. Okay. Now, as I mentioned, distinguishability I'll explain when we are doing a problem. That becomes much more easier. So, okay, or just to give a hint, I wanted to introduce a term RT and RP. So, for a simple circuit like this, okay, this is the high frequency regime, this is the low frequency. Sorry. Just give me a moment. You have something like this, okay, a single one. So, at high frequency, whatever data you get is like this is RS value, okay. So then where is the RT value and RP value? For a single circuit, the RT and RP value is remaining to be equal. Now, when it comes to two circuits or something, this becomes RS value. Because at the highest frequency, whatever data you get, that is corresponding to double capacitance. So after that, whatever happens is the Faraday equation. So in that region, of the higher frequency regime, whatever data you get, that is RT value, and at the lower frequency. So we always know for your data, this becomes a high frequency regime and this becomes a low frequency. There's a mid frequency, right? So this is always RP where it meets, but in the single circuit, RP and RP value remains the same. Now, when two circuits happen, when two semicircles come, this value here is RP for sure. Low frequency regime, the value, if even if the circuit is like this, we have to extend it or what to say, in Z7, you can try to fit it and the value where it hits the what to say the x-axis is RP value. Even if it is not complete, you can try to model it, try to fit it with RC elements, and then the equipment will give the fitting. The Z7 software can give you what is the RP value. Now, this value corresponds to RP value. Okay, this is about RP and RP value. Now let's look into the distinguishability method. Or I think it is still good to explain with the question in the assignment section. Then that gives you better understanding. So I'll go for that. Okay. Now the next one is zeros and poles. So after this, we'll be just going into the little theory part, and then probably if, like in 10 minutes, we'll be starting the assignment questions. So for any electrical circuit, I mean for any data, you can express it in terms of zeros and poles. Okay. Now, for example, I'm giving a circuit. It's actually a combination of the distinguishability quotient. So that's why R5, C6, R6. Now, what is the total impedance? R5 plus this, they are in parallel. So we have to do 1 by, so this part was like 1 by j omega c plus 1 by r6. So that is j omega c plus 1 by r6. This is in parallel. So if I take the reciprocal, this becomes 1 by j omega c plus 1 by r6. Now let me just simplify it. R5 1 by j omega c r6 plus 1 r6, right? Then if I again simplify it, R5 j omega c R6 plus R5 plus R6 j omega c R6 plus 1. Now this equation has both zeros and poles. Okay. This portion is called zero. You get the zero of the equation from the top and the poles from the bottom. Poles. Now how do you find it? Equate them to 0. The top one equal to 0. That is this one equal to 0, this one equal to 0, and find out what is omega value. That's what you have to do. So like R5 plus R6 plus j omega R6 R5 C6 equal to 0. Now omega value is nothing but minus of R5 plus R6 by j C6 R5 R6. Similarly, 1 plus j omega R6 C6 equal to 0 and omega equal to minus 1 by j R6 C6. So this is 0, this is the pole. Now, this is about finding out the zeros and poles. But what is the physical significance? You have an equation, what do you get from the zeros and poles? That exactly is the disadvantage. You can represent the system using zeros and poles. So basically the zero by pole that will give you the system. You have the system using that particular numerator by denominator. But what's the significance? Okay, that exactly is the difficulty of this method. You cannot relate the significance of the zeros and fours to the system. You cannot bring out a physical significance, so that becomes a disadvantage. Okay. Last portion. Okay. Then we'll be looking into the assignments. Limitation of EEC. So as I told, when you get an inductor, okay, or sometimes the data can go into the second quadrant. Okay. In all these cases, you need to use negative resistance. Okay. Uh, so giving a meaning, assigning a meaning becomes difficulty. Okay. Not difficult. If you are good at it, I mean, there are people who work on it and they are able to bring out a physical significance. It's good. But otherwise, without a meaning, simply fitting into any circuit, it doesn't make any sense. So that is one of the limitation of equivalent circuit fitting. Then finding out the optimal values. Okay. If your initial case is poor, then the error will be very high. So how exactly you have to give the values, that also requires, you're gaining it over the practice. So that is another disadvantage of the econometric circle. Okay. So yeah, with this we have come to the end of you know a discussion on what was taught last week. Now last week meaning this week's assignment. Now we'll be directly moving on to the assignments. Let me take the assignment. Question one. I'll be writing down the question. Complex plane plot of impedance spectra is given below. So I'm drawing the circuit here. Start somewhere here. It's 100, this is 200. Besides, they have also given 50. Yes. Hello. Hello. Alright. Sorry. ഞാനിപ്പോ ഇത്തിരി തിരക്കിലാണ് 5 മിനിറ്റ് ശേഷം വരാം. So this is the plot. Yeah. Now the circuit starts somewhere here and it ends somewhere between 250 and 300. Okay. Now you have to understand, try to understand, or your question is which circuit can be used to model it. Okay. Yeah. So first thing, it is not starting from origin. So how to understand or try to find out the answer? Origin, it's not starting. So it means there is the initial RS value. Solution resistance exists. So that is modeled using a resistor. Right? Now the next question is, now the next part is, that's the first thing to understand. So you have a solution resistance. Now you have a single loop. Single loop means one RC, right? So one RC means you have one capacitor and one resistor in parallel. So your answer becomes something like you have one resistor with a solution resistor, or sure it is R5. Okay, they have given many options, and apart from that, you will have one capacitor and one resistor in parallel. So which of them is this option there in the question? Yes, it is option B. So there they are given, this is R5, this is C6, this is R6. Okay, so this can be used to model system. So if the here, so always from the x-axis origin to the value at which the semicircle starts. Okay, that one will be the solution resistance. So based on what we understand till now, this value is Rp and Rp. So can anyone tell what is the value here of solution resistance? So I can say this almost in between 0 and 50. I'm saying it is in the middle. So this value something becomes 25. So I can say RS value is 25 ohm centimeter. Okay, it's only given in ohm. The units are ohm. So ohm. Now what about RT and RP? Because of a single loop, RT and RP value are same. Okay. The end value, that is 250 and 300. It is in between that. Let me say it is 275. But is the value 275 alone? Is it 275? No. Why? Because it's not starting from the origin. It is little away from the origin. How much away from the origin? 25 ohms. So basically the RT or the RP value is nothing but this value. Because it's a what to say, a single loop, RT and RP value remains same. And that is 250. Oh. This is how from the circuit to try to understand what is RT and RP value. I hope this is clear. Now let's move to the next question. The complex plane plot of the impedance spectrum is given below. And your circuit is something like this. Okay. And then this minus Z imaginary. So the question is, at first, which of the following circuit should one employ to model the spectrum? Okay. So how did we do now? Same thing goes like same like this. So first, it doesn't start from the origin. Okay. That means you have a solution resistance. Now after that, how many loops are there? This is the first loop. This is the second loop. This is the third loop. Right? So there are three RC circuits. So always the first loop corresponds to the double layer capacitance. So I have something like this. Now let me look into the option. So I should have three pairs of RC. Okay. So it can be either what to say. You have this an option. This is one pair, right? This becomes one pair. This is RS. This you cannot include. This is the first pair. Then you have this next pair. Then you have the next pair. So is this there in the option? Yes, option number C. No. Is this the only one you can use to fit the data? No. You can also go for a ladder circuit. Ladder circuit. Here also you have what to say three pairs. This is the first pair. This is the next pair. This is the next pair. So three pairs of RC is there. You can either go with this one or this one. Yeah. So here your circuit has an inductor, but you're still using a resistor capacitor in parallel in order to fit it because you know that you can fit an inductor using RC if they are allowed to go to negative values. So yes, this can also work. Now, how to find out for such system what is RP and RP value? It is little not complicated, but if I explain that, so let me use this Maxwell circuit. So for this system, if you want to find out what is RP value, this is the solution resistance. It has nothing to do with the reaction. It is simply avoided. Similarly, this is the double layer capacitance. So this will also be avoided if I'm talking about the Faraday reaction. So this is what corresponds to the Faraday's reaction. Okay. So now I have to find out what is RP, what is RP. Okay. Uh, to do that, what I'll do is let me name this R1, R2, C2, R3, C3. Now, RT is when omega tends to infinity. What happens to omega tends to infinity? Resistor, no change, right? It is R is not dependent upon the frequency. But what about the resistor of a capacitor? Resistance of a capacitor, let me write as ZC so that you guys don't get confused. ZC. That is J omega C. Omega tends to infinity, meaning ZC value becomes small. ZC value is 1 by J infinity C. That means it is becoming small, zero. It offers no resistance. So what happens is, it will have the tendency to pass through those circuits in which, through those lines in which the resistance is very low. So here the current comes like this, can go here, here, here. This offers no resistance. C2 offers zero resistance. This offers zero resistance. So this becomes something of the form R1, R2, R3. So the resistance is becoming 1 by R1 plus 1 by R2 plus 1 by R3. This is the value of RT. Now consider the case when omega tends to 0, that is RP. Omega tends to 0, ZC values what? 1 by J, omega becomes 0, C. That becomes infinity. It offers infinite resistance. That means no current can pass through capacitor. So there are three ways can pass through this line, this line, this line. There is a capacitor. This blocks the passage of current. C3 also blocks the passage of current. So all the current can only pass through R1. So RP becomes R1. So this is how you have to find out what is the RP value or what is the RP value when you are given a system. Okay, RP like when omega tends to infinity, 1 by j omega c tends to 0. That means it offers very negligible resistance. It can pass through the capacitor. So if it is RP, that is omega tends to 0, the capacitor offers infinite resistance, cannot pass through the what is it, the path in which capacitor is there, blocks the passage of current. So current can only pass through the alternate path. So that's how we have to find out the RP and RP value. Okay, this was an additional information. Okay. Now the third question is an important question where you will be looking into distinguishability. The question is consider following circuit. Here R3 equal to 1000, C3 equal to 100 microfarad. Let me convert it 100 to 10 to the power minus 6 farad. R4 equal to 250 ohm. You have to find the value of the elements in the equivalent circuit. Okay, this is the question. Now let me plot. R3, C3, R4. These values are given. Now you have to find out R5, C6, R6. Yeah, this is how you have to do. I mean, sorry, this is the question you're supposed to do. Now the first question is what is the value of R5? All the questions are linked. The question 3, find the value of R5. Question 4, find the value of R6. Let me write in a single page. Okay. Your question 3 is to find out the value of R5. Question 3. Question 4 is to find out R6. Question 5 is to find out C6 in microfarad. Okay. So all the three questions are linked, hence that I'll be solving them together. Now what should we do? So I already told when you say they are distinguishable, what does that mean? It means that the total impedance of the circuit are equal. So let me find out what is the value of the impedance of the first circuit, that is R3, C3, R4. So this is the methodology of the flow law. Now first let me find out the impedance of this part. This is R parallel. Sorry, Z parallel. How do we do this? This is Z parallel. Okay. Now Z parallel or Z. Okay. Z parallel. Okay. I'm writing as ZP. They are in parallel. So what I have to do is I have made a mistake in the question. So yeah, that was what I was wondering. Sorry, I just rubbed it. It's not R3, it's not outside. Then what is the difference? I mean, both the circuit that I drawn were same. I didn't notice actually. It's only when I started to write it, I noticed it. Okay, let me redraw it. Three, R4, C3. So here, R3 and R4, they are in series. So in that line, Z series. So let me name this as Z series. Z series or ZS. So ZS equal to R3 plus 1 by J omega C3. Why J omega C3? Because they are in 1 by J omega C3 is the resistance from a capacitor and that is in a series with the resistor. Now, this entire thing is in parallel to resistor 4, right? So when the two networks are in parallel, it is always good to solve it in admittance mode because in admittance mode, when they're in parallel, you have to add up. It's basically opposite of in solving an impedance mode. So for that, what I'm doing is this line and this line, I'm going to solve. They are in parallel. So because they are in parallel, I'm going to solve it in impedance mode. Okay. And when I'm solving it in impedance mode, it becomes what? I can do it in, sorry, if I'm solving it in admittance mode, you have to take the parallel. So parallel means 1 by this entire value plus 1 by r. Instead of doing that, it becomes easier. If it becomes same actually, but before that, let me also simplify this. Simplify this means R3 J omega C3 plus 1 by J omega C3. So when they're in parallel, I can either add it up simply using admittance mode. Uh, so, or I can simply take the parallel how we do for in the impedance mode. I'm going to do the impedance mode. Sorry, admittance mode. I'm simply writing Y dash. Y dash becomes 1 by R4 plus 1 plus ZS. Not Z as YS. But then, okay, I'll just simplify it instead of doing this. I can either go for they're in parallel. I can either go it in admittance mode where I'm simply adding the admittance of each of the arm, or I can do the consider them in parallel and then add up the admittance form. So either of that way it will actually work. Okay, so presently I'll go with the normal impedance mode itself. They both are in parallel. So I'll write it as ZP. So ZP becomes, because it is in parallel, I have to take inverse 1 by R4 plus what is the reciprocal of 1 by ZS. So 1 by R4 plus J omega C3 by R3 j omega C3 plus 1. Now, what is the Z parallel? It becomes 1 by R4 plus j omega C3 by R3 j omega C3 plus 1. This is one term. Okay. The Z parallel is nothing but the net impedance of the entire circuit. So the net impedance I can write it as 1 by R4 plus j omega C3 by j omega C3 R3 plus 1. Now, what is the for easy, in order to make this easy, this impedance should be equal to the impedance which we get when we are solving this equation. That's how we find out R5, R6, etc. But before that, let's simplify. Let's simplify in the sense, what will be the impedance when omega tends to 0? When omega tends to 0, how can I write Z value? There won't be any change for R4. But what about this? This entire term becomes 0. It becomes equal to R4. This is for your understanding presently. Now, same way when omega tends to infinity, Z double dash becomes 1 by R4. Because there's no change for like R doesn't have an effect from the frequency. Now, what I'm going to do is from the next term, I'm going to remove the j omega. So you have j omega plus C3. Same if I'm removing from the denominator, I'll get j omega C. Sorry, j omega C3 I'm going to remove. So here it becomes j omega C3 into 1. Here down it again becomes j omega C3. If I remove this becomes 1 R3 plus 1 by j omega C3. This is cut, this is cut. And this term tends to, when omega tends to infinity, this becomes equal to 0. Why? Omega tends to infinity, this becomes, entire term tends to 0. So you get 1 by R4 plus 1 by R3. Now if we solve, we are already given R4 value as 250 ohms. Okay. Now 1 by R4, 1 by R4 plus 1 by R3. The values of R4 is 250 and this 1000. If you solve it, you will get the value as 200 ohm. So this is the approach. You are first given a circuit whose all the values R4, R3, C3 are given. Find out the total impedance. Okay. Then find out the impedance when omega tends to 0, when omega tends to infinity. Do this much. Now let us move on to the other equation or other circuit which we are having. What is it? You have R5, you have C6 and R6. You don't know any of the value. Do the same thing. Find out the total impedance. So this both are in parallel. Let me take 1 by Zp equal to 1 by R6 plus 1 by j omega c, which is 1 by j omega c6. Now you have to simply multiply j omega c6 R6 j omega c6 R6 and Zp value becomes j omega c6 R6 by j omega c6 plus R6. Now this is in series with R5. So the total impedance is R5 plus Zp R5 plus j omega c6 r6, j omega c6 plus r6. Now, omega tends to 0. What is the value you are getting here? Z value equal to how much? Omega tends to, this means R5 will come. This value will become 0 equal to R5. Now, when omega tends to 0, here the omega value is 250 ohm. So equate both of them. R5 should be 250 ohm. Are you able to get it? So basically, you have two circuits which are saying as distinguishable. So that means the total impedance of that system should be equal to this. And again, the impedance, when you're simplifying it using the conditions omega tends to 0, omega tends to infinity. Whatever value you get for omega tends to 0 here should be equal to the value which you will get over here when omega tends to 0. Now, that's how you found out R5. Now, how to find out R6? Same thing. For omega tends to infinity, what is going to be Z? R5. So as I did before, we'll take out j omega c6. We'll have R6 by again j omega c6 1 plus R6 by j omega c6. So this term tends to, okay, what should I repeat? Could you please tell? Okay, you have, the question is, you are asked to consider a circuit, okay, where you know the value of R3, C3 and R4. You know all the three values. Now you have another circuit where you don't know the value of R5, C6 and R6. But you know that they are equivalent circuit. What do you mean by equivalent circuit? I had given you an example before where I told, wait, let me see. Yeah. 3 RC loop means there are three loops, you need 3 RC. You can either fit it using a void circuit, you can fit it using a Maxwell circuit, you can fit it using a ladder circuit. But shouldn't the circuit be unique? No. What did we mean? What did we tell there? We meant that the circuits can be interchangeably used. Interchangeably used means they are distinguishable in terms of the values of R and C used, but the same system, your impedance circuit can be fitted using any of those circuits. So same way here they have said that these two circuits are distinguishable. This is your assignment question number 345. So they have given you the value of R3, C3, R3. They have asked you to find out the value of R5, C6 and R6. Okay. So I know they are distinguishable, but they can be used interchangeably. This means the net impedance from one circuit should be equal to the total impedance from this circuit. But that doesn't mean that the value of R, C will be same over here and here. The values of R and C can be anything, they will change. But the total impedance will be same in both the cases. So how did we approach this question? We'll first find, so that also means total impedance, okay, of this circuit and this circuit will be equal. That is first thing you have to understand. So you don't know what is R5, C6 and R6. What you should do is you have to find out the total impedance in both the circuits. They should be equal. Because you know the value of R5, R3 and R3, R4 and C3. Right? Using those values, you can find out the total impedance of first circuit. Equate it to the next circuit and then you can find out the values of the resistor and capacitor in that circuit. That is the first point. Next, we also saw we can use two cases. Once you find out total impedance, the next thing you can do is you can find out omega tends to 0, omega tends to infinity. There are two such cases. So what you will do is the total Z you got, let me say that is ZT. You can find out what is the impedance when omega tends to 0 and what is omega tends to infinity in either cases. Then you using that conditions you are simplifying and finding out some equation either side. They should also be equal. So you have three unknowns, you have three cases, find out individual values. So what did we first do? For the first circuit, I know all the values. I found out the total impedance. This was the total impedance. Simply first week what we did, solve and find out the total impedance. This becomes your equation 1. Next, to the same equation, apply omega tends to 0. Omega tends to 0 means omega is becoming 0 in the total impedance. This term becomes 0 and you will find out one more value. R4, you will get the value. R4 value is already given in the question as 250. So when omega tends to infinity, the impedance value that you get is equal to R4, that is 250. Now, the next circuit where you don't know the value of R5, R66, same way, find out the total impedance, then find out the impedance at omega tends to 0. When you simplify it, you will get in terms of some resistor. From the first circuit, when you simplify it, you found out that value equal to 250. Equate it, find out the value. Now, same way, omega tends to infinity. Simplify the first circuit, this value, you will get the value. Because you know R1, R2, those R3, and R4. You are able to find it out. Now, the same thing, I'm going to repeat it for the next circuit. Is that clear? Okay, so this is the approach we're going to do. First circuit, you know the individual resistor and capacitor value. You are able to find out the total impedance. After that, simplify it using omega tends to 0, omega tends to infinity. Next circuit, I don't know the value, but I'm finding out the total impedance first. Now, the next step, find out the impedance when omega tends to 0. Find out the impedance when omega tends to infinity. That is the next step. So, this is the total impedance for the second circuit, where you don't know the value of R6 and R5. Now, substitute. Now, so equate omega tends to 0 in this equation. So when you simplify it, it becomes R5 here. This omega tends to 0. This entire term tends to 0. This becomes R5. But when you solve the previous, previous circuit where you already know the values of R4 and all, you found out when omega tends to 0, Z value is 250. We said it's distinguishable. So the value which you get here should be equal to what you get over here. So automatically R5 becomes 250 ohms. Is that clear? If it's not clear, you can again mention it. I'll explain again. Okay. Now you have to find out what omega tends to infinity. Same way I'm simplifying it. This omega tends to infinity means 1 by 8. Good. So 1 by omega becomes 0. This value tends to 0 and you will get R5. Just give me a moment. Yeah. So you got R5 plus R6. Okay. And from the previous example, previous circuit, this omega tends to infinity. The value was how much? 200. See, it was written 200. So this value should be equal to 200. And we know R5 from the previous equation, I know it is 250. So R6 becomes minus. Just give me a moment. Yeah, R5 plus R6 equal to 200. So, sorry, R5 plus R6 is how much? Sorry, 1 by 250 plus 1000. I think I have made a mistake in the calculation over here. 1 by 1000. Just let me try that. 1 by 4 by 1000 plus by 1000. No, 1000 by 5 is 200, right? Yeah. So that's 200 ohms. And we know this R5 is 250, right? R6 value is supposed to be minus 50 ohm. Okay. This is the value I'm getting. But I'm not sure. In the solution, it is given as 50. But I'm getting a negative sign. I think I have done this right. I may have to check again and then I'll get back to you. But I'm getting a negative sign. At least in the question, it's not given negative. That's what I'm checking. Just give me a moment. I'll check and get back to you for the next class regarding this. But this is the method by which this has to be solved. Okay? Yeah. Now, just give me a moment. Let me just think this. Omega tends to 0. The value you get is R5. Okay, just yeah. I think I've made a mistake. From this part, I'll explain once again. Yeah. So here, when we are writing like this, and uh, instead, okay, we got an equation something like this. That is, do not, okay, as per the, just give me a moment. I'll just, yeah. So here, 1 by ZP is 1 by, okay, ZP equal to 1 by R6 plus 1 by, sorry. Okay, so here is where I made the mistake. So Z parallel is 1 by R6 by what to say 1 by j omega 6, right? So here I made the mistake. So here it is 1 by, so yeah, I made a mistake there. So that is nothing but this j omega c6 because this is 1 by j omega c6. This is r6. When I'm taking the reciprocal, it becomes 1 by r6 plus 1 by j omega c6. So just like this. Okay. This is the Z parallel value. Then Z total value will become R5 plus 1 by R6 plus J omega C6. So I made a mistake over here in calculation. You should be careful. So then, so your equation is Z total equal to R5 plus 1 by R6 plus J omega C6. Now when omega tends to 0, your it becomes how much? R5 plus R6. Now, why? Because this term becomes 0 when omega tends to 0. So, 1 by R6, it becomes R5 plus R6. Now, what is the value when omega tends to 0 here? It is R4 equal to 250. So this is your first equation. Now, omega tends to infinity. your Z double dash value will become R5. This entire denominator will tend to infinity. So 1 by infinity equal to 0. Now what is the value for the previous circuit when omega tends to infinity? Omega tends to infinity, it becomes equal to how much? 200. So R5 equal to 200 ohms and R6 equal to 250 minus 200 equal to 50 ohms. Yes, we have corrected it. So be careful when you are simplifying it and finding the total circuit, what to say, impedance. Okay. Now we have two values, two circuits. Now how do you find out the value of the capacitor value? What you have to do is you have to equate the total impedance from both the sides. So Z1, that was from this. So that one, I'm simplifying 1 by 1 by R4 plus j omega C3 by j omega C3 R3 plus 1. If I'm simplifying, what I can do is I can cross multiply this. Please do it because of the time, because the time is short, I'm just simplifying it. Simplifying in the sense, I'm just cross multiplying and making it into, numerator by denominator form. Please try it, and if anyone has any doubt, you can ask me in the next class. You will get something like this. Now, same way, find out for the next circuit where you don't know the value of R1 and R2 and R. That is R5 plus 1 by R6 plus j omega C6. What I'll do is I'll just multiply this here and take R6 up. So it becomes R5 plus R6 by j omega C6 R6 plus 1. Now both this impedance should be equal. That is what distinguishability means. So I know what is the value of R4, R3 and C3. Substitute. R4 was 250. You can look into the question. R4 is 250, R3 1000, C3 100 microfarad. Substitute all the value. So you will get, so simplify this. Now this should be equated to the next equation. R5 value is 200, R6 is 50. Now simply equate it, rearrange it. Okay, and once you solve it, because of the time lag, because time is we are running late on time. I'm not showing the mathematical calculation. I'll show you how we are deriving it. Now you see in either side you will have j omega. Okay, you have to write it in terms of j omega. Finally, so in one step, you will write something like this 2500 j omega c6 equal to 6.25 j omega. Why? Because other terms are all numerical numbers, they will get cancelled out. So j omega will get cancelled, and this you will get as 2500 microfarad. This is how you have to solve the question. Because of the time, because we are running late on time, I'm not showing you the derivation. But mathematics, you have to be clear, you have to solve. But this is the approach you have to do. Now, this one. The next question is, so 3, 4, 5 are done. Now the next question is R3, C3, R4. You have one equation, and the next one you have R4, R5, and sorry, R7, R8, and L8. Same like the previous one. This part is same, right? The values are also same, I think. Yes, R3 value is same, R4 value is same, C3 value is also same. Now, same like the previous one, you have to find out R7, R8, L8. How do you do that? How we did previously. Find out. So this portion is same. You don't have to. This portion is same. Equation same as previous one. So you write the Z total. Then you have Z dash. Then we have that is omega tends to 0. Then you have Z double dash and omega tends to infinity. Those values stay same as what you got from the previous one. Now for this one, you will have to again solve it. How? You have to find out the total impedance. What is the total impedance? In the parallel circuit, it becomes Z parallel inverse. It becomes 1 by R8 plus 1 by J omega L8. Right? Then Z parallel becomes 1 by R8 plus 1 by J omega L8. Then total Z will become R7 plus ZP. From this, you will do this. Then after that, what you have to do is the Z2 if I say. It's for second circle. Then omega tends to 0. What is Z2? Find omega tends to infinity. What is Z2? You have to find it. Then you have three equations. So Z1 total will be equal to Z2 total. If you equate it, you will find out the inductor value from this. So this two can be used to find out the resistor value. Same like previous question. It is a similar one, so you have to do it carefully without making. I can give you some what to say. If you're solving it properly, okay, you the answer I'll give. Your R7 value will be equal to R4. R8 will be equal to minus R4 square by R3 plus R4. And finally, L8 will be minus C3 R4 raised to square. When you're doing it, make sure you're getting these as the relation. Same as the previous question. Okay. Yeah. Now, the next question is consider the spectra. The spectra is something of this form. They've asked to find out. So, if I'm modeling this using this circuit, this question number 9, R1, C2, R2, R3, and C3. The circuit can model this circuit can model spectra provided. The question is option A, value of R3 is negative. Option B, C3 is negative. Both of the above, none of the above. So we already told when we are trying to model an inductor using resistor or capacitor. So what should be the product, like both our resistor and capacitor should be negative. So option is C. I have repeated it multiple number of times here. Okay. Now the next question number 10. You have a circuit like this. Okay. And you see there are three loops. One loop, there's two loop, there's three loop. So you are modeling it using this is the first, this is the next RC, this is the next RC. So this is R4, C4, R3, C3, R2, C2, and R1. Now, the question is, the circuit can model the spectra if R2 is negative, R3, C3, or R4, C4 is negative. That is, either one of them is negative, both of above, B, none of above. So the question is not fully clear because what is both of the above, right? That is with respect to option B, they are asking. Either you want R3, C3 or R4, C4 to be negative, or both should be negative, or none of them should be negative. So the answer here is, so you see in the second one, second loop, that's an inductor. So that if I say R3, C3 should be negative. Why? Because you're modeling an inductor. Now let me come to the next loop, that is R3. Here Z real is also becoming negative. So I can say R4, C4 should also be negative. So here the answer is both of the above. Okay, I hope that is clear. Now the next one, I see a circuit like this. They have asked me to find out the value of RT and RP. Okay, here this is 0, this is 20, this is 40, this is 60, this is 80, and this is 100. So I know what I have to find out, what is RP, what is RP. So we know directly RP. So this is question number 11, this is question number 12. Let me go to question number 12 first. We know omega tends to 0, we get RP value, which is nothing but this point, right? This point is RP. So it is coming between 80 and 100. I can say it is 90. But is it directly 90? Why is it 90? Because it's starting from in between 0 and 20. It's not starting from origin. So RP value is this value, not from the origin, from where it starts till then. So if I say that is 10, your value is going to be 80 ohms. Now what is the value over here? So here if I am, now what is RT value? Where the first loop is meeting the x-axis. This part is RT. Let me say this meeting somewhere here. I'm just extrapolating. So if it doesn't meet the x-axis, I can extrapolate and find it out where it is meeting the x-axis. So here I'm telling it is 40 minus 10 equal to 30. These are the values. Okay, 11 and 12 questions are done. So yes. So now the next question. I'm again given a circuit. It's 5 microfarad. This 1000 ohm. This 250 ohm. This is again 250 microfarad. This is minus 500 ohm. This 100 microfarad. Okay. Now, what is the RT value? This is question number 13. So, in this one, as I told, this is what is Faraday reaction. 100 ohm corresponds to solution resistance and 5 microfarad corresponds to double layer capacitor. So, I have to only consider this part. Now, if I simplify it, not simplify, if I write there is one here, one over here, and 1 over here. So current can go like this, and it goes like this, like this, like this, and it comes out. Now, goes like this, or it can go in either three parts. When RT tends to 0, sorry, when omega tends to infinity, you get RT value. So 1 by j omega c will tend to 0 when omega tends to infinity. That means capacitor offers negligible negligible resistance. So this means the current can pass through this circuit, this one, and this one. This is like it's not there. It offers no resistance. It's easy to pass through. So RT is nothing but I have one, then the next thing 250, and the next thing is minus 500. All of them in parallel. So if I solve 1 by 1000 plus 1 by 250 plus 1 by minus 500 raised to minus 1. Because this is in parallel, so raised to minus 1 because I'm taking the reciprocal. What is it? It's in parallel. 1 by 1000 plus 1 by, so 1 by RP value will be 1 by 1000 plus 1 by 250 plus 1 by minus 500. RP value will be plus, I mean RP no, RT value will be reciprocal. And when you solve this, you will get 25 amps. Sorry, 1 by 1000, 1 plus 4 minus 2. You will get around 333.3 ohm. Now the same question to find out RP when omega tends to infinity, which is question number 14. Okay. So you have one here, you have one over here, one. Okay. This is 1000 ohm. What happens when omega tends to infinity? 1 by j omega c. Sorry, RP means omega tends to 0. 1 by j into 1 by 0 becomes infinity. That means this path won't allow any passage of current. Same over here. So RP value is nothing but all the current should pass through this one. So answer is 1000 ohm. Right? So I hope whatever we discussed till now was okay for you to understand. Hmm? If any doubts, we'll discuss it in the next class. Okay. Otherwise, we'll be stopping the class for today. So we looked into the distinguishability, how to find out if one circuit is given, how to find out the other values, etc. So that's what we saw today mostly. So if we have to next part, we will see for the next class. Okay. Any doubt, we'll discuss in the next class. Thank you.